So what we can do now that we have our two straight line solutions, our quote unquote straight line solutions, we can actually put them together and manipulate them in a way that will make it meaningful for us on the phase plane. So what I mean by that is something along the lines of this, where we have our general solution has two parts. The first part is our first eigenvalue with eigenvector, and our second eigenvalue and eigenvector. And all I did here was I kind of expanded my exponential, and just remembering that a plus b and the exponent can be split up like this. So with a little bit of manipulation, we can end up with this. And you'll notice all I did here was kind of expand using Euler's expansion for both of those two. And it's worth noting here that over here the negative does stay from the eigenvalue up here. The negative does stay inside the cosine and the sine. But if you remember your trig, cosine of a negative angle is the same thing as cosine of a positive angle. So this really is the same thing as cosine of 2t. The other one, sine of negative 2t, is the same thing as negative sine of 2t. So it's just a little trig identity there that we're going to make use of. So once you've got that, the next line, all I did was kind of put together, I used my vector notation here, and I pulled this thing inside, multiplied it by the top, multiplied it by the bottom. And so this first matrix right here is what we get when we do that. And you'll notice that e to the t is a kind of constant for the whole thing, so I'm going to pull that out front. And then by multiplying it through like this, you can see I've got 2i times k1 times cosine of 2t. That's this times the 2i. And then the other term has got an I in it. So we're going to wind up with negative 2. That'd be 2 times I squared, which is negative 1. And so after a little bit of work on both of these terms, I did the same thing over here. And I went ahead and underlined each one of the terms that has an I involved. And so those are they contain the imaginaries. And so what I'm going to do on the next line, the next stage here, is on the top, I'm going to group together the blue underlined things. And on the bottom, I'm going to group together the blue underlined things. I can't mix and match vertically, but I can combine horizontally. Everything is multiplied by e to the t, so that's not a problem. And the next line gives us something like this, where we have the imaginary containing values over here in this matrix, and then these are all just real values. Now you'll notice that I've got 2i minus 2i, and what they're multiplied by is k1 cosine 2t, k2 cosine 2t. And then down here I've got I times k1 and I times k2. So the next line, and same kind of thing over here, the next line down, what we're going to do is, excuse me, grab up our coefficients. And we factor out a cosine 2t, we factor out a sine 2t, factor out a sine 2t, and a cosine 2t, and we get something that looks like this. Now at this point, it kind of looks like we have, well, just a cosine term and a sine term in the top, and sine and a cosine term in the bottom. The other thing that's worth noting is up here we have k1 plus k2 times negative 2, and in the bottom k1 plus k2. So whatever this constant is, the top is just 2 times it, or negative 2 times it. Over here, I times k1 minus k2 appears down here, but 2 times that appears in the top. And this is where kind of the magic happens when we get to say I is a constant, k1 and k2 are constants, so this thing right here, that's just some constant, and this is 2 times it. And over here, whatever k1 and k2 are, that's just a constant, and this is negative 2 times that. So the kind of tricky move that we make is if we let constant 1 equal I times k1 minus k2, and constant 2, I'm just going to use c here. Then if C2 is K1 plus K2, then this top is negative 2 times it. We wind up with this as our general solution. Now, if you're looking at this and thinking, okay, all of this is a lot of algebra work, all to simplify to get down to here. and keeping track of a whole bunch of terms. Now, we can rewrite this if we want in parametric form, if we prefer to see it that way. But it means the same thing. There's a top equation, that's my x of t, and my bottom equation, that's my other variable, y of t. Now, I don't know if it's x and y. I'm just making up those two dependent variables. But that's kind of important for us, because what we've just discovered is if we start with our two eigenvalues and our two eigenvectors, we can simplify to get a general solution. But here's the kicker. We could have, rather than manipulated this thing, we could have gone way back to the beginning. And if you remember in the previous video, we got to this point where we had our straight line solution, and I said we could use both of them, but we could have actually just used that one. And this was the kind of the sneaky way that I did in the lecture notes. I said, we don't need both of those. We just need one. And the reason that it works is if I grab my one straight line solution and expand, here's my straight line solution number 1, e to the lambda 1 times its eigenvector. And then I expand that and use my Euler's formula. And then my next step is I'm going to multiply this through top and bottom. It looks like that. And you notice right away we've got imaginary and imaginary values and then real terms. And so we can kind of pull those apart into the real and imaginary terms. And the trick that I played in the notes is to just say, hey, look, this looks like it's two parts of a solution that are not linear multiples of each other. And so we just throw a constant in front of both of these. And sure enough, if you use that trick and you just throw a constant in front of the real part and a constant in front of the imaginary part, and just imagine that I gets absorbed in that second constant, then you wind up with this, which looks pretty familiar. And sure enough, the top, you notice it's -2 on the top and 1 on the bottom, 2 on the top and 1 on the bottom. And sure enough, that's what my x of t and y of t would be in this situation. Now, paying close attention, that looks an awful lot like what I had at the end of my previous paper. And so notice we've got a 2 times a constant 1 and then a constant 1, cosine and sine. 2 times a constant and then a constant, cosine and sine. Bring back the other one, -2 times a constant with a sine, the constant and cosine. -2 times a constant with a sine, a constant, same constant with a cosine. These two solutions are identical. Now, you may look at it and think, oh, that's just as easy. But I would argue the amount of work that goes into manipulating this thing to get the solution compared to this to get the solution, no question, this one is much, much easier. And so that's why I prefer to say use the one straight line solution, quote unquote, and expand that one. But notice, up to this point, it's really still the straight line solution. It's me using this point right here and saying, oh, there's a real part and an imaginary part, so I can throw constants in front of those, and it does work. But that's when the general solution appears. Up to this point, it's still just a straight line solution, a particular solution, right? When we put the constants in front of it, that's when it becomes general, and then we can write it like this. So that gets us to the end of this example, which we started off here. And if you can find the eigenvalues, you only really need one. And find an eigenvector, you only need one. And if you have one eigenvalue and its associated eigenvector for a complex eigenvector combo, then you can just jump right in and use that quote-unquote straight line solution method. Expand it, and then you've got your general solution. So it's bookkeeping, but it's actually a whole lot less bookkeeping this way. Hope that helps.